Hello everyone, myself is Dr. Vinke Sutaria, working as an assistant professor at Department of Chemistry, Bhavans College, Dakor. So in our previous lecture, we have studied about the some basic terminology of photochemistry, and we have seen that some of the important factors related with the photochemistry, such as total energy, the formula of total energy, why translation energy is not considered, what is the quantification of that translation energy, and the diagram that we have studied about the how rotational energy, translation energy can be defined as. So now in today's lecture we will study about the one of the most important diagram of photochemistry, that is Javalsky diagram. Now this Zabalski diagram, it is very much important as far as the photochemistry point of view as well as your exam point of view. So before going to the this diagram, let us understand how the photochemistry or light and matter can interact. So I have given this basic chart. You can also write down in your notebook that when light and matter means any type of compound, okay, any type of compound, that is matter, light and matter interaction, then there is two possibility, whether they can scatter or whether the light will be absorbed. Now if they scattered, then it is known as Rayleigh line, or if they are inelastic, so they can known as Raman line or Brillouin line. So this is not in your syllabus, but you should know light and matter interaction. If the light and matter interact with each other, there is two possibility. First one, that is scattering, and second one, that is absorbance. In scattering you will find a Rayleigh line and in elastic point of view, and if it is in inelastic, then it is Raman or Brillouin lines. Okay, so now we are talking about the absorbance. Now in absorbance we have studied about the UV spectroscopy, and now absorbance point of view. Now what is absorbance basically? So absorbance can be categorized in the photoluminescence. Photoluminescence, there is two possibility, whether it is of fluorescence or phosphorescence. Now they can be electroluminescence or thermoluminescence or chemiluminescence or bioluminescence. So these are the luminance point of view. Okay, so photoluminescence, now they are having two category, that is fluorescence and phosphorescence. This is for only your basic knowledge how light and matter interaction they can follow by the scattering and absorbance, and elastic inelastic, Rayleigh line, Raman line, fluorescence and phosphorescence. Okay, so you should know, you should have an idea about the light and matter interaction. So there is a possibility they have designed that scattering and absorbance can be classified further. So now let us understand the Jablonski diagram. So what is Jablonski diagram and how it can be drawn and how it can be understood? So this is the basic diagram of Zabalski diagram. You can pause the video, you can write down, you can draw this Zabalski diagram, and you should understand the each and every part of this diagram. Then and then you can have an idea about the photochemistry. Normally what happen, we have simply said that when we give the light in terms of UV or in terms of photochemical reactions, what will happen, ground state electron will travel to the excited state. That is our normal what we can say idea about the light and matter interactions, but it is not certainly like this. There is so many possibility, there is so many mechanism in between to the ground state to excited state and coming back to the ground state, so that we have to understand. So let us understand by this diagram. So here I have drawn here in this picture you can see that the S0, that is the ground state level energy. Now when we excite the S0 state, it will goes to the excited state, that is S2. Okay, so now in absorbance what will happen, whatever the excitation wavelength is there, the emission wavelength is similar. What is the excitation and emission? Emission, that is the come back to the ground state, that is known as emission. So if the excitation wavelength and emission wavelength both are similar, then we can say that there is the absorbance. Let me give you the example. Suppose if we take the graph of UV spectroscopy. Okay, now if any molecule, as we know the range of UV, that is 200 to 400 nanometer. Okay, so now if any molecule excite the if any photochemical reaction happens and it excites the molecule at the range of 253 nanometer, let's say example of 253, so the emission wavelength is also will be the 253. Okay, so if it is a 253 nanometer, let's say this is a 253 nanometer. Okay, so in absorbance, okay, or in UV spectroscopy, absorbance in UV spectroscopy, what will happen? So absorbance excitation wavelength as well as the emission wavelength both are similar. Excitation means ground state to excited state. Emission means what? Excited state to the ground state. So that is the difference. Both the wavelengths should be same. So excitation wavelength as well as the emission wavelength should be same. Okay, so now what will happen? So in the absorbance, the molecule will get excited. Now as we know, by giving the energy in terms of the photochemical condition, what will happen? There will be the vibrational, there will be the rotational, there will be the electronic transition, there will be translation energy. So after this, it falls to the S2 state, it is the excited state. Now in between that there is a vibrational level, this is the vibrational level. Okay, so it falls back to the higher excited state, ground state. Remember this word, that is higher excited state, ground state. Now by giving this, if you are following this, it will goes under the internal conversion. Internal conversion means higher excited state to the lower excited state. Now S1 can be the lower excited state. Remember the word, this is the ground state, this is the excited state. Now this is the higher excited state, this is known as higher excited state. Now by giving the energy, it falls back to the ground state by means of what? Internal conversion. Now this internal conversion, S2, the state will be converted into the S1. Now it interconvert to itself. What will happen? Both the energy are differ. Now again they falls back to the vibrational level, internal conversion, vibrational level, and if it is falls back the higher wavelength to the excitation wavelength, then it is known as fluorescence. Okay, again I am repeating, the energy molecule will get excited. Now they will interconvert itself and they will have a lower excited state by means of vibration relaxation. Again they are falling back to their actual ground state. Okay, now if the wavelength is higher than the excitation wavelength, then it is known as fluorescence. Okay, what is fluorescence? So you should remember this word, that is in means of the absorbance. Okay, now in absorbance what will happen? Excitation wavelength is equal to the emission wavelength. Okay, now in fluorescence, okay, now in fluorescence what will happen? That emission wavelength is higher than the excitation wavelength. That means when we're talking about the fluorescence, the range of the fluorescence, it is 200 to 800. In between that 200 to 400, that is the excitation wavelength, and 400 to 800, that is the emission wavelength. Now when we excite the molecule, let's say suppose this molecule excited nearby 260 nanometer. Okay, so now this molecule when it comes to the ground state, at that time the wavelength will be higher than the excitation wavelength. Suppose if it is having a 440 nanometer, so now this 440 nanometer is higher than the excitation wavelength, then you can say that the mechanism should be of fluorescence, not the absorbance. Why? The absorbance phenomena, that is the excitation wavelength and emission wavelength, both are similar. Now what is the definition of fluorescence? So generally the fluorescence can be defined as emission of photon, okay, that is emission of photon without changing its multiplicity, without changing its multiplicity, then it is known as fluorescence. Okay, what is fluorescence? Now emission of photon, that is emission of photon, okay, that is the emission of photon, that is the emission of photon from its excited state to the ground state without changing the multiplicity. The singlet or S1, that means singlet, this is also singlet, but this is the higher excited state, this is the lower excited state, and this is the ground state. Now both are having S1 and S2. The multiplicity is not changed. Multiplicity, that is the singlet, doublet, triplet, whatever. So that is will be the multiplicity. Now the emission of photon, this is the emission of photon without changing in multiplicity. Okay, then it is known as fluorescence. Okay, so here lambda 2, here lambda 3, here you can put down that is the lambda 1. Okay, so that is the difference between the absorbance as well as the fluorescence. Now what will happen? The another level, that is the terminology of phosphorescence. Now when a photon, okay, now when the photon come back from the its excited state with changing of its multiplicity via intersystem crossing, that is known as ISC, that is intersystem crossing. This is known as IC, internal conversion. Now here what will happen? This singlet state is converted into the triplet state. Okay, and then it falls back to its ground state via vibrational relaxation. Then it is known as phosphorescence. Okay, again I am repeating. When emission of photon, the similar type of definition you can put down over here. Okay, what is phosphorescence? So the phosphorescence can be defined as emission of photon, that is emission of photon by changing its multiplicity is known as phosphorescence. Okay, by changing its multiplicity it is known as phosphorescence. So that is the basic difference between the fluorescence and phosphorescence. Here the similar type of excitation wavelength is lower than the emission wavelength. Second one, emission of photon by changing its multiplicity is known as phosphorescence via intersystem crossing. Now you should remember that is the difference between the intersystem crossing and internal conversion. Internal conversion, that means the S2 that is converted into the S1, higher excited state, higher singlet excited state converted into the lower singlet excited state, that is known as internal conversion. Now what is intersystem crossing? The intersystem crossing, that means conversion of singlet state into the triplet state, then it is known as intersystem crossing. Now this is known as singlet excited state, this is known as triplet excited state. Okay, so now via internal and external conversion they will again come back to its ground state. Now this lambda 4 it is for the phosphorescence, this lambda 3 that is for the fluorescence, and this lambda 1 that is for the absorbance. Okay, now that is the difference between the absorption, fluorescence and phosphorence. Again I am repeating that what is absorption? The absorbance means that the excitation wavelength as well as the emission wavelength both are similar. What is fluorescence? Now fluorescence can be defined as emission wavelength is higher than the excitation wavelength. Second one, the definition of fluorescence, that emission of photon without changing its multiplicity. That means S1 to the S0, S1 to the S0 without changing its multiplicity is known as fluorescence. Phosphorence, emission of photon by changing its multiplicity, is known as phosphorence. Okay, now in examination they will ask the long questions of 6 marks to 8 marks about the description of a Javalsky diagram. So first of all you should draw this diagram, and then after you should explain all the terminology and write a point of view. Again I am explaining you each and every step or each and every terminology of Jabalsky diagram via elaboration. Okay, so what will happen to this Zabalski diagram, or actual reaction mechanism, what we can call in the light and matter interactions. So when a molecule has been promoted photochemically to an excited state, it does not remain there after a long time. Most promotions are from the S0 to S1, so that is from this level to this level. Okay, now in promotion to the S2, the higher singlet state, that is what we can call as S2, S3, further we can call as S4, okay, takes place, but that is only in a liquid, or it can happen into the solids. It cannot be going to the gaseous. Okay, now these higher states usually drop very rapidly to the lowest, that is S1 state, because the lifetime of S2, S3, etc. is usually less than 10 raised to minus 11 to 10 raised to minus 13. Okay, there is a very what we can say lesser time. Okay, suppose if we excite this molecule to the S2 level, now this molecule cannot remain a longer period of time at the S2 level. It has to come back to its ground state. The remaining time, or what we can say the lifelong time of S2 level, that will be the 10 raised to minus 11 to 10 raised to minus 13 seconds only. Okay, the energy lost when an S2 or S3 molecule drops to S1, that is this level. Okay, now S2 to S3 is given to the medium. Such a process is called as energy cascade. Okay, this is also you should know, that is known as energy cascade. Energy cascade means what? The transition from S2 to S1 via internal conversion you can call as energy cascade. Okay, now in the similar manner, the initial excitation or the decay from higher singlet states initially populate the many of the vibrational level of S1, but they are also cascade down to the lowest vibrational level S1. And this cascade is known as vibrational cascade. Why it is known as vibrational cascade? Now this S2 via vibrational level it falls back to the ground state of the S2, then by internal conversion it is converted into the S1, again it is converted into the vibrational level, it falls back to the lower state of the S1. Now there is known as vibrational cascade. Okay, the period that any electron or any molecule can be remain at the excited state will be 10 raised to minus 10 to 10 raised to minus 13 seconds. Okay, you should remember that whatever I am speaking to you, you should able to write down. Okay, by pausing the video, after watching the video 1 or 2 times. Okay, whatever I am giving, because it is not very convenient to write down all the things. Okay, I will provide the notes also, but you should remember that whatever I am telling to you, you should be able to write down in a notebook and make a proper note of that. Okay, now step by step we will be getting terminology of this Javalsky diagram. So a molecule in the S1 state can cascade down through the vibrational level of the S0 level. Okay, now this S1 falls back to the its ground state, that is the S0 level, and thus return to the ground state by giving up its energy in a small increment to that surrounding. But this is generally quite slow because the amount of energy in between the what we can say S0 and S1, this S0 and S1, okay, is large. This process cascade is called as internal conversion. Okay, now what is internal conversion? The conversion of S2 to the S1, okay, within the period of time of 10 raised to minus 11 second to 10 raised to minus 13 second, it is known as internal conversion. Okay, now the electron will come over here. Now what will happen? The lifetime of this S1, okay, this is the lifetime of this S2. Now this S1 lifetime, it is nearly about 10 raised to minus 9 to 10 raised to minus 15 second. Okay, that S1 levels, that is the measurement, that is 10 raised to minus 9 to 10 raised to minus 15 seconds. A molecule in the S1 state can drop down to the some lower vibrational level, so that will be the S0 level. Okay, now by giving of the energy in the form of light, this process when generally happens within the 10 raised to minus 9 second. Okay, so now if it is happen in the 10 raised to minus 9 second, okay, 10 raised to minus 9 seconds, then it is called as fluorescence molecule. Okay, again I am repeating, 10 raised to minus 11 to 10 raised to minus 13, that is the lifetime of the S2. S1 state, the lifetime will be 10 raised to minus 10 raised to minus 15, 10 raised to minus 9 to 10 raised to minus 15. Now if it is falls back around the time period of 10 raised to minus 9 seconds, then it is known as fluorescence. Now this pathway is not very common either because it is not because it is relatively slow. Expect a smaller molecule, that is a diatomic molecule, okay, and rigid molecule. Now this rigid molecule, I will be explaining you what is rigid molecule. Now benzene, it is not a rigid molecule, but when we are attaching one more ring to the benzene, then it is known as rigid molecule. Why? Because of these two carbon atom, it is quite common between these two rings. When I am attaching one more ring, it will become a more rigid. Why? Because there will be a 4 carbon atom attaching to each other, then it is known as rigid molecule. Okay, now this is the fluorophore. What is fluorophore? It can give the luminance, that is why it is known as fluorophore. That is all other branch of the spectroscopy, it is a fluorescence spectroscopy, that is not in our syllabus. But here you should remember that when we are having 10 raised to minus 9 second lifetime, then it is certainly for the fluorescence. Okay, for compounds that compound shows the fluorescence emission spectra are usually approximately a minor image of the absorbance. Okay, now the difference between the fluorescence spectra as well as the what we can say UV visible, now that is the range of UV and this is the range of visible. Okay, 200 to 400 UV, 400 to 800 visible. This is the excitation wavelength and this is the emission wavelength. Okay, so both are similar as comparatively the range point of view, but there is a drastic difference between these two phenomena. In absorbance you will find excitation and emission wavelength is similar. Okay, so now after doing these things, what will happen? This comes out because it's a fluorescence molecule dropping down the lowest vibrational level, so that will be the S1. Okay, so again come back to the S1, then come back to the 0 level, that is the S0. Okay, so now that is the description point of view of the fluorescence. Okay, now what is intersystem crossing? So the most of the molecules in the S1 state may drop down to the triplet state. So this S1 state converted to the triplet state. Okay, now by doing these things, what will happen? The multiplicity is changing. Here they are having a S1 state and it is singlet state, it is converted to the triplet state via means of what? Intersystem crossing. Okay, that is called intersystem crossing, the conversion of S1 to the T1. Okay, now this S1 to the T1 state, for every excited singlet state there exists a corresponding triplet state. Okay, suppose if you are talking about this singlet state, there is always the possibility of the triplet state. But what will happen, since transition from excited singlet state S0 to triplet, populating the triplet state, the efficiency in ISC, that is intersystem crossing, depends on the difference in the energy between the small the ISC is sufficient. So when we are having a difference between low lying singlet state and triplet excited state, what will happen, this S1 to the T1 state, okay, this S1 to the T1 state, the energy, the singlet to the triplet state, transition from that S0 to the T1, it is quite forbidden. Forbidden means what, it is not allowed transition. Okay, so the lifetime of this triplet state, okay, now this triplet state, it is nearly about 10 raised to minus 5 to 10 raised to minus 3 seconds. Okay, a molecule in the triplet state may return to the S0 state by giving up the heat. Okay, now ISC, that is the non-radiative process. Okay, non-radiative process. Okay, now this non-radiative process or light, this is called a phosphorescence. Now this is known as phosphorescence because of the changing of the multiplicity. In fluorescence there is no change of the multiplicity. Okay, so now when fluorescence and phosphorescence occur in the same type of molecule, that time we can found at the lower frequency than fluorescence because of the higher difference in the energy between the S1 and S0 as compared to the T1 and S0. What will happen, suppose if you take one example, like suppose if I am having one molecule, let's say A molecule. Now in this A molecule, when we are having a fluorescence as well as the phosphorescence, so here the fluorescence energy is higher than the phosphorescence energy. Why? Because if you can find out over here, there is a small gap between the conversion of the S1 to the triplet, but what we can call that okay, so now that is the smaller difference between this S1 and T1, but when you compare this S0 to the T1, there is a large difference. So the phosphorus energy is lower as compared to the fluorescence energy. For many molecules, when it is compared to the intersystem crossing, is not very efficient. If this is the only way to produce T1, then T1 would be rather very limited. Okay, so when we compare to the S0 to conversion of T1, so it is very difficult to convert the triplet state, and it has the limitation. Okay, fortunately triplet state can be populated by the use of donor molecule. Donor molecule is a substance whose intersystem crossing. Okay, what is donor molecule? Donor atom or donor molecule which can donate the electron. Okay, now this donor molecule transfer its large amount of energy to the acceptor molecules. Okay, you should remember this thing, acceptor molecules. Okay, the difference is that it gives the electron, it accepts the electron. So that is the donor molecule and this is the donor acceptor molecule. Okay, now this excited state of singlet or triplet of donor molecule transfer its large amount of energy to the acceptor molecule. Now in this process, acceptor species promoted to the excited state and donor species return to the ground state. So what will happen, now when we are having a donor atom, now when we are giving the photochemical reaction, it will excite this molecule, that is the D star. Okay, now what will happen, this donor molecule, okay, the energy of the donor molecule is accepted by the acceptor molecule. At that time what will happen, the acceptor will get the excitation. Okay, although photons are absorbed by the D and it is A which becomes excited. This phenomena is also known as photosensitization. Okay, you should remember this. What is photosensitization? Okay, what is a photosensitization? Okay, what is the photosensitization? So now the D accept the energy from the photochemical condition, it get excited. Now this excited molecule, when it contact with the acceptor molecule, now excitation molecule of the A, okay, by losing the energy of the D. Okay, now this phenomena is known as photosensitization, or D is referred as photosensitizer. Okay, now D is also known as photosensitizer. Okay, why? Because it helps A to excite the molecule. So that is the difference between these two things. Okay, now this transfer of energy from these things, from donor to the excitative, how it proceeds. Now let us give by example. Suppose if D is having a 2 electron. Okay, now when it gets excited, what will happen? It converted into the D star. Both the electrons are similar. Okay, now what will happen if it goes to the intersystem crossing? Now these two electron will get excited via intersystem crossing. Okay, so now what will happen? Both the sign of these molecules or sign of this electron will be the similar. Now it means a plus one half or minus one half. It means plus one half and plus one half. Okay, now when you put a formula of 2Ni plus 1, okay, to 2s plus 1, sorry, multiplicity 2s plus 1. So what will happen here? So here we can have a 2 into plus 1 half into minus 1 half, so it will be 0 plus 1, so it will have a singlet excited state. But when we calculate this thing, what will happen? 2 into plus 1 half plus 1 half, that will be the 1 plus 1, so it will have a triplet state. So that is the difference. Here you are having the electron, that is plus 1 half and minus 1 half. But when we go for the intersystem crossing, what will happen? Both the electron signs are differ. Both the electron signs are the similar. So the multiplicity will be the triplet. Here the multiplicity will be the 1. Okay. So now let us understand. Now why doing this thing? When it again accept the molecule from its excited state. Now donor will have the excited state. Now acceptor molecule will also have the similar type of the notation of the electron. Now what will happen? This acceptor molecule accept the electron from the donor atom. So now the acceptor molecule, which is having a triplet excited state, again donor atom will falls back again the ground state, which is having the similar type of notation. So this is the difference between these three. This is the thing. Okay, donor atom excited itself via photochemical condition. Now again it goes to the intersystem crossing, change its multiplicity. Now this changing its multiplicity is known as phosphorescence. Now again the acceptor molecule accept the electron from the donor atom. What will happen? The acceptor molecule get excited and it has the triplet excited state. Now donor atom, which is falls back to the ground state. Now this donor atom, which is having a singlet excited state. Okay, so now this will happen. Now this photochemical condition, what will happen? Now suppose if it is having, let's say suppose this acceptor molecule, okay, now it is having a triplet excited state. Now via photochemical reaction, okay, via photochemical reactions, it converts these things to the product. Okay, now it is known as sensitization. This is known as sensitization. But what will happen to this donor atom? Okay, that we should also know. Now donor molecule, which is having, suppose let's say this type of notation of electron. Now it converted this thing to the product. Okay, by means of the quenching. What is quenching? Okay, so quenching phenomena, that means a loss of fluorescence. Okay, now loss of fluorescence, that is known as quenching phenomena. you have already known this thing. Suppose when we are talking about the radium, okay, what will happen to the radium? Now whole day the radium absorb the energy by means of the sunlight, okay, by means of the sunlight, okay. Now radium will shows its fluorescence at dark side, or we can say in night, okay. When we are having a night, okay, when we are having a dark side of that particular room or particular what we can say the environment, at that time radium will glow, okay. We have radium will glow. Now that luminance, okay, that luminance is known as fluorescence. But in the what we can say in the morning you will find the similar type of radium will not glow. Why? Because it absorbs the energy by means of the sunlight. Now when we are having when we are not having any sunlight, at that time it will glow. So when it glows, it known as fluorescence excitation, okay, fluorescence, okay, that is the enhancement of the fluorescence. But when when it do not have when it does not have any types of luminance property, at that time we can call as the quenching, okay. You have already seen this radium plate on the bike, in the bike, or what we can say the banner, okay. So what will happen to the radium? So radium absorb the energy in the morning in the sunlight. After that what will happen at the dark? It will glow, okay. That is known as fluorescence enhancement and quenching. When it is glow, then it is known as enhancement, okay. When it falls back to its ground state, okay, in the morning, then it is known as quenching. The similar type of things happen in the rigid molecules like naphthalene, anthracene, anthraquinone, pyrene molecule, quinoline molecule. When we are having a fuse ring, okay, the excitation and emission will be there, okay. So now this is all we can say about the Zabalski diagram. The method of the sensitization has been proved to the enormous value, as it provides a value of group potentially reactive intermediates, okay. So now this is all we can say about the Jablonski diagram. So let us summarize this thing. In the summary we can put down that physical process that undergoes the excited molecule. So what will happen? But when we are doing a summary of this theory, okay, now what we have studied, suppose when S0 state, okay, now when it does the photochemical condition by means of the photochemical reactions, so it will get excited, okay. S0 will convert into the S1. Now this phenomena is known as excitation. When S0 converted into the S1, again this S1 vibrational level of energy, when it is converted to the S1 state by loss of the vibrational level and generation of heat, okay, that is known as vibrational relaxation, okay, that is known as vibrational relaxation. Now this S1 state again come back to the S0 state by giving the H mu, then it is known as fluorescence, okay. What is fluorescence? Emission of photon from the excited state, that is the excited state, to the ground state without changing the multiplicity is known as fluorescence, okay. Now let us understand this S1 when it is converted into the S0 by loss of heat, okay, then it is known as internal conversion, okay. Now it is known as internal conversion IC. Now this S1 when it falls back to the triplet state by a loss of heat, okay, that is known as vibrational relaxation, okay, via vibrational relaxation. But when this triplet state falls back to the S0 state, that is the ground state, by a loss of heat, that is known as intersystem crossing. Okay, now this is known as intersystem crossing. Now this S1 state, okay, when it combines with the acceptor molecule of the S0 state of the acceptor molecule, now when it converted to the S0 state plus acceptor molecule higher excited state, then it is known as singlet transfer photosensitization. Singlet transfer of photosensitization. You can write down in the bracket. Okay, now when triplet state combines to the acceptor molecule S0 state, now this S0, when it falls back to the triplet state of the acceptor molecule, then it is known as triplet. Then it is known as triplet transfer. So you can, in your two things you have to remember in Javalsky diagram. First of all, you should write down the, you can draw down the Javalsky diagram properly. Then after, in the last segment of your question, you should write down this summary. So examiner can have a brief idea that the students is knowing all the factors and all the terminology of the of the Javalsky diagram. Okay, so thank you for watching it.